All right, good afternoon. Today is Duality Day, when we see this most important and powerful theorem, perhaps in all of combinatorial optimization. If you remember last time, we started off from studying linear systems, linear equalities, and we had, where did it go? We had a kind of duality expression for linear systems, right? Exactly one of the following holds. Either you can solve a linear system, or you can find a proof that you cannot solve the linear system. Yes? And then we took some time talking about sort of the structure of polytopes. And we talked about vertices and extreme points and such. We gave these three different characterizations of the corners in terms of intersections of independent constraints, in terms of the unique optima of an objective function, right? Or in terms of points which are not on the inside of the polytope, that are not convex combinations of other points. But then we started talking about this most important thing, which is duality. Okay? And I introduced this notion of duals by looking for bounds on a linear program. So what we eventually arrived at was, if we have a solution that is feasible for a standard form linear program, and we have a solution that is feasible for a canonical form linear program with the same matrix, right? Then we know that YB, which is the objective in the canonical form, right, is equal to YAX because of the way that X satisfies the constraints, right? But since YA is less than or equal to C, and X is all non-negative, this is less than or equal to CX. So the objective of the standard form linear program always upper bounds the objective of the canonical form dual to that linear program, right? So the primal linear program is lower bounded by the dual linear program, and conversely, the dual linear program is upper bounded by the primal linear program. Right? It's completely symmetric. And in fact, which one we call the primal and which one we call the dual is arbitrary, because they play the same role with each other. Okay? And so this fact was known as weak duality. Right? And it's nice. It's nice to be, right? If you're trying to minimize something, then a lower bound is a useful thing to have. Okay? But what we're going to be spending today proving is that it's a really good lower bound, but in fact it's tight. Okay? Again, subject to some very minor conditions, which I will shortly get to. strong duality says that assuming some simple stuff, that in fact the optima of these two linear programs are equal. Okay. So before getting into that proof, let's do a little sanity check. What is the dual of the dual? Okay. So we had this process for constructing the dual of the original linear program. What if we apply that process to the dual that we got? Okay. Now, our process only worked for a standard form linear program, right? So what we're going to do is we're going to convert our dual, our canonical form dual, into standard form, and then see what happens when we apply the transformation, right? So we had this dual where we say we want to maximize yb such that y is less than or equal to c. But we want to make this standard form. So we're going to transform that into a minimization problem. And we are going to add some slack variables. Right? This is way back when we were introducing on the video linear programs. They showed how to transform something into a standard form. So we added these positive slack variables to replace the less than or equal constraints with equality constraints. Right? And then we needed to split, in order to have the y greater than or equal to 0 constraint, we had to split into the positive and negative parts of the variables. So we write this as the positive parts minus the negative parts, such that the positive parts times A minus the negative parts times A plus S is equal to C. And now everything can be non-negative. Right? So this completes the transformation into a standard form linear program. And if you think about this in matrix form, in matrix form, you're basically looking at your positive y's, your negative y's, and your slack variables being multiplied by minus b here, plus b here, and 0 here, such that you've got, shoot, I'm going to get my transposes backwards here. So again, y plus, y minus, and s times a minus a, and the identity matrix is supposed to be equal to c. Okay, that's just the matrix form of the constraints that I just wrote. So now that we have it in standard form, we can apply our technique for taking the dual, right? And so when we take the dual, what we get is maximize a CZ such that, right, because C is the constraint on the right, so it turns back into the objective in the dual, just like it did in our original dualization, right? That's the easy part. And now our constraints are that are that A minus A I times z, the dual variables, are at most minus b, b, and 0. Because again, when we go from the primal to the dual, the right-hand sides of constraints turn into the objective function, right? And conversely, the objective function, which is what we see here, turns into the right-hand side of the constraints, right? And the matrix is unchanged, right? I mean, sorry, I transposed it, but it's the same matrix, okay? But now you see that essentially we're stating the same constraint twice, right? A times z is less than or equal to minus z, and minus a times z is less than or equal to b, right? Those are basically saying the same thing twice. And so all we're really asking for is here I have a minus of the maximization problem, so I'm going to turn it into a min of a minus of a negation of that. And the constraint is that a times minus z should be equal to b. And you see we also have this constraint that I times z is less than or equal to 0. That's just saying that z is less than or equal to 0. Right? And so this is almost what we want. All I now need to do is replace minus z and turn it into some z prime. Or let's call it w so that I don't have to fight with primes. And so now this is min cw such that aw is equal to b, and w is greater than or equal to 0. So we took the dual of the dual, and we ended up with the primal again. Okay? So I probably made a math mistake somewhere, but this traces out the derivation, and you can redo it yourself carefully if you want, if you don't trust me, which you shouldn't. So any questions about that? Again, it was just a sanity check that it really is a dual. One of the characteristics that you want in a dual is that if you apply it twice, you get back to where you started. And so that is true of our dual process. Okay, so the dual of the dual is the primal. Now let me come back to weak duality for a minute. We said that the dual is always upper bounded by the primal. Let's unpack that a little bit. There are 4 possible duality situations. Okay. Depending on, and this is where we get the technical conditions for strong duality. In general, we think of the sort of linear programs that we're working with as being feasible. There has to be we expect that it will be a point, and we're trying to find the best one. We also prefer to think about them as being bounded, so that we don't have optima that go off to infinity. But for completeness, we have to think about both of these cases, right? So if P and D, the primal and the dual, are both feasible and bounded, then we have exactly what I wrote over there, that yb is less than cx. We really do have upper and lower bounds on each other. Okay. Now, another possibility is that P may be feasible. Okay. If it is, that is going to make D either infeasible or bounded. Okay? If P is feasible, it provides a bound, and that prevents the dual from being unbounded. Right? If P is feasible and unbounded, what can we say about the dual?
Yeah? It's
then the dual has to be infeasible. Right? Because if the dual were feasible, it would provide a bound on the primal, and so the primal could not be unbounded. Okay? So we are going to write this as the primal value, or as the value of this linear program being minus infinity. Okay? And let's think about whether that makes sense, right? The primal is supposed to be, the primal is a minimization problem, right? So being unbounded means it can get arbitrarily small, so we denote that by a minus infinity. Okay? The reverse can also happen, right? D can be feasible and unbounded. And that makes the primal infeasible. And we write that value as plus infinity. Okay? And notice that these kind of make sense for the other side as well, right? So when we say the value is minus infinity, we look at this dual, which is a maximization problem, right? We're saying that there's no number you can achieve because it's infeasible, right? Similarly, in the other direction, if it's the dual that is unbounded, that's a maximization problem, so it can get arbitrarily large. Meanwhile, saying that the primal has value plus infinity is saying that it can't achieve any number at all in its attempt to minimize. Okay? The only other possibility is that they might both be infeasible. Okay, and then we don't, I mean, hopefully we don't run into those because they're not very useful, right? But they don't really fit into our notation. There isn't a value that really makes sense if you want to talk about them both being infeasible. Okay? But if we X out this one, right, strong duality is just saying that for all of the other cases, feasible, unbounded, infeasible, right, it's just saying that the minimization problem, or the minimization problem which we see in the primal in this case, is lower bounded by the maximization problem that we get from the dual. And the plus and minus infinity numbers work there as well. Okay? So it's quite concise. Okay? And so really these are the four cases, right? That both values are finite and equal, or that both values are plus infinity, or that both values are minus infinity, or finally, that they're both infeasible. Yes?
Did you just say equal, or am I just
Sorry, the strong duality is that they're equal. Thank you. The weak duality that we've already proved is the inequality, but we're about to embark on a proof of the equality. Okay? Any questions? All right. So I sort of set this up. I said, this is the most technical, mathy result that we're going to do all semester. There's no algorithms. It's all math. But I really don't like math, so instead I'm going to do physics. So I'm going to prove strong duality to you with pictures. Okay? So here we go. Right? So let's draw a picture of a linear programming problem. Okay. What I'm going to do when I get my linear programming problem is I'm going to go to the shop and get a bunch of boards. And I'm going to construct I'm going to construct the polytope in wood. And then I'm going to turn it so that the objective function is pointing straight up. And now how am I going to solve the optimization problem? Well, I'm just going to drop a ball into the polytope that I've built. Okay? And of course, it will be a zero-dimensional ball, but that's a little hard to draw, so here's our ball. And, sorry, this is going to be B. So one thing I'm doing that's not quite in line with my notes is I'm actually starting with the dual linear program. Okay, I'm going to take the dual of this linear program. Okay? And I'm also, you notice, I'm inverting. Like over there, we had expressed the dual as a maximization problem with a less than or equal. I'm just flipping the sign of everything because gravity doesn't point upwards. Okay? So now, what do we learn by applying our knowledge of physics to this, to this shape or to this arrangement, right? Intuitively, the ball lands at the optimum of this polytope. Why? What was that?
Gravity.
Gravity, right? So gravity represents the objective function. It is pulling the ball down, right? And the minimization objective is saying we want the ball to be as low as possible, right? But where it gets interesting is when we ask, why did the ball stop? Let me call this position y star. That's the optimum. Why does the ball stop there? Yes?
The force of gravity is balanced by the force applied by those sides.
Exactly. The ball is stopped by the application, by the forces that are coming from the constraints, right? Right? I don't even remember what the notation is for the force of gravity, so I just made one up. Okay? So the ball stops because the constraints exactly cancel out the force of gravity. Right? Now, what are those forces? What kind of force does one of these, I should say frictionless, wooden constraints? I varnished it really well. What force is exerted by a particular constraint? Yes?
Force?
Exactly. Okay. So each constraint exerts a force that is normal to the constraint. If you think about it, each of these constraints, right, it's expressed by a column of the matrix, right? When we say that YAI is greater than or equal to C, AI is that normal vector, right? And you'll notice I've pointed that normal vector in the direction where greater than or equal is the correct, is the correct sign. Yes? Okay. In other words, the ith constraint generates a force in the direction of AI, right?
Why is the direction of
You mean why physically is it in the direction of AI?
I mean, why mathematically?
Well, it is the normal vector for this particular plane, right? The way you define a constraint, the way you define a plane is by giving its normal vector, and that's what shows up in the columns of these constraints. Okay? So that's the direction. There's also a magnitude, right? Now, we don't know right now what that magnitude is. So let's just give it a number. Yes? So now that I've written down these variables, these values, how do we express mathematically the notion that the forces from the hyperplanes exactly cancel gravity? Yes?
We would say that Fg is, or I guess that the sum of all of these forces, the sum over all I, AI x I is Fg.
And what value represents the force of gravity in this picture?
I guess minus B.
Correct. Correct. Except we're canceling, right? So in fact, the sum of these forces has to be equal to B because gravity is minus B, right? In other words, Ax equals B. Ooh, okay. We're getting somewhere, right? Okay. Is there anything else that we can say about these forces, about this picture? Well, which hyperplanes can exert these forces? Or sorry, which planes can exert these forces? Can it be any plane? Yeah?
Has to be the planes that the ball could land on.
What do you mean by could land on? So the ball is in a particular place, right?
Yeah, what I mean is they can't have their normal going in the direction of B. Or sorry, against the direction of B.
Ah, good. So yes, in general, you could imagine that there's some hyperplane over here whose normal is upside down. That's just sort of outside of the scope of our intuitions. Let's not worry about that right now. Okay? It would actually have to be up here, because if it was down here, you would make the polytope infeasible. But let's not worry about that. But like, you know, I drew, I guess, six planes, right? Which of them are exerting forces on the ball? Yes. 2. Which ones? These 2. Why? Great pointing. That was like so accurate. I saw exactly what you're. Why are these 2 the ones? Why do we know that these are the ones exerting force on the ball? Yes.
They are touching the ball.
They have to touch the ball, right? We're not doing magnetism here. These are wooden, right? Now, how can we turn that into math? Yes.
Constraints are tight.
Yes. These are the tight constraints, right? Now, before I write that down, I skipped a small step. Can we say anything about the values xi, these magnitudes? Yes. They're non-negative. Why? Because the walls push on the ball, right? They don't pull on the ball. So we also have that xi is greater than or equal to 0, right? But now we just made this point that to exert the force, you have to be tight on a hyperplane, right? Which is to say that, oops, change page. That if YA is greater than C, if it's not tight, then xi is equal to 0. Okay? So let's look at what we have here. We have ax equals b, and xi is greater than or equal to 0. You put those together, what does that tell you? about these x's? Yeah?
A feasible solution to the
Exactly. The forces are a feasible solution to our primal linear program. Right? Now this, that ya being positive makes xi 0, that's actually a complementary slackness condition, if you remember from what we talked about with min-cost flow. And I'm going to show you that that leads to optimality. Okay? So y greater than c implies xi is greater than 0. So a very compact way to write this is to say that c minus, sorry, I left off some stars here. So that's the optimum y. So c minus y star times a times xi is equal to 0 for all I. Let's check that. Okay? So there's two cases, right? If yi is greater than c for a particular column, a particular hyperplane, right? If you're loose, then xi is equal to 0, which means that the product of these two quantities is equal to 0, because xi is equal to 0. On the other hand, if y is equal to c, then it doesn't matter what xi is, because this term is 0, and so again, the product is 0. Okay? So if I sum this over all of the different, I, right, this tells me that c minus ya times x, or dot x, is equal to 0. Okay? But now we're actually home free, because that implies, right, here we have, what this is telling us is that, that cx is equal to yax, right? But what is yax? Or what is ax? Yeah? It's equal to b, so this is in fact equal to yb. Okay? So just thinking about the nature of the forces tells us that our x is feasible for the primal linear program. I started with the dual, so x is the primal, and x is feasible for the primal because of the nature of the forces. When we then bring in this other observation that the forces can only apply from hyperplanes that are tight, that tells us that the values of the two objectives are equal. Okay? And I guess I again need a y star here. And now we're done, right? Because we had weak duality already, right? We knew that one objective can't be smaller than the other, and now we show that they're not separated, that they're equal to each other, and that's the strong duality result. So, any questions? Does everybody buy the argument? Yes.
So you say these two objectives are equal, but we are maximizing one while we are trying to minimize the...
Correct. They are equal at these parts, right? What I've shown you is that at the optimum, right? When you are at the optimum y, that generates a set of forces which produce an optimum x. Okay? Or to put it another way, right? There are two feasible points. There's a feasible primal point and a feasible dual point that have exactly the same objective value. And because they're exactly the same, that means both of them are optimal.
So what about the other vertices? Like
Well, there are plenty of other vertices, right? But you won't be optimal at those vertices, and you won't have a balance of forces, right? At any other vertex, the ball will want to roll.
So did you use any condition where it only applies when this ball is at its optimal?
Yes. Where did I apply the optimality of the position of the ball? Yeah?
With Y star.
Exactly. But what property of Y star came from the fact that the ball is in an optimal position? Yeah?
Sum of AI and size.
Exactly. It was this force cancellation, right? That force cancellation happens because you're at the optimal position, that there's no place that the ball cannot go any lower. Yes?
Could you explain again why this Y star AI is greater than C means that the constraint is tight?
Well, remember, the constraint is that YA is greater than or equal to C. Right? So the definition of tightness for that constraint, right? If YA is greater than C, it means the ball is not touching the hyperplane. YA equals C is the equation of the plane. So when YA, if you have a Y star so that Y star A is equal to C, that means you're actually on the plane. Yes?
Why complementary slackness leads to the objectives being equal? Like everything seemed really intuitive until the final part.
Why does complementary slackness lead to the objectives being equal? So it provides the pathway to this argument that this is one of these when you know something for too long, it becomes intuitive, right? So let's see. Why does complementary slackness is often the pathway to proving equality of objectives. Can I add to that intuition?
What is complementary slackness?
Complementary slackness is this statement right here. It says that the complementarity is that if the constraint is slack, then the corresponding variable is 0. Okay? And again, this is something that you'll develop intuition for as we work on duality. But one of the sort of most basic things about duality is that a constraint in the primal turns into a variable in the dual. And a variable in the primal turns into a constraint, or corresponds to a constraint in the dual. Okay? So here we have a constraint, a hyperplane in the primal, and that that corresponds to a particular force magnitude exerted by that constraint in the dual. Okay? And in a sense, and this can be formalized, this force magnitude sort of tells you how sensitive the primal was, or sorry, the dual was in this case, to changes in the constraint boundary. Like if I change C, sorry, this should be CI. If I change CI by a little bit, if I move the hyperplane, that's going to change the value of the optimum, right? And what the XIs are measuring is how far is the optimum going to move, how much higher is it going to get when I move the constraint by a certain amount. And if the force is very large, then moving the constraint by just a little bit will also move the ball by a lot. If the force is very small, and again, in 2 dimensions, this is pretty natural, right? What's going to be exerting a large force? A hyperplane that's nearly flat, right? And so if I move that hyperplane, it's going to move the ball by just about the same amount, right? If, on the other hand, the hyperplane is nearly vertical, it's barely going to be exerting any force, right? And in that situation, moving that hyperplane is not going to raise the height of the ball very much. Okay? Yes?
So the reason why this ball being at a minimum and the sum of the forces equal in gravity is like an if and only condition is because otherwise this shape sort of wouldn't be convex. Is that right?
Right. So again, this is physics. It's not a proof, right? And one of the things that we sort of slipped right by is this convexity, right? There's only one of these lowest points, right? We proved that. I mean, it comes from convexity, but you can't infer that from my picture looks that way, but my picture doesn't prove that there's only one optimum, right? Yes?
Why were you talking about the boards being vertical and horizontal and their forces?
Well, again, this is just tied to this notion of complementary slackness, okay? That complementary slackness is kind of a binary condition. Either that, right, if the constraint is slack, then xi is equal to 0. But there sort of is a stronger version of it that says that xi, when it's non-zero, measures the sensitivity of the optimization problem to changes in its input. Okay? So xi is a measure of the sensitivity of changes to ci. Okay? And of course, when xi is 0, it means that there's no sensitivity, right? You can change ci and it won't matter. Why won't it matter? Because the plane isn't touching the ball, so moving it doesn't change the optimum. Okay? All right, so that's the physics, but we're not physicists. So now that we have this relatively intuitive argument, I'm going to mostly formalize it for you in math. But let's take a little break first to kind of get our brains ready for the formal.
And I was going to ask if we considered this a physics, CS, or math proof, but I guess it's more physics.
This is the physics, and after break, I'll show you how to translate this into math.
Oh, okay. I was just gonna ask because I don't think I've ever actually seen a rigorous proof.
Well, mine will not. I would not say that mine is going to be totally rigorous, but it is certainly going to have enough math that you can see how to make it rigorous.
Okay, that makes sense. Thank you.
Sure.
For the duality situations, is it possible for the primal to be feasible and bounded, but for the dual to be infeasible?
Primal, feasible, and bounded, and dual infeasible. I don't think so.
I was wondering if, like, in the first situation there, are you saying if and only if the primal is, or if the primal is feasible and bounded, then the dual is feasible and bounded, or are you just saying that both of them being?
No, if the primal is feasible and bounded, the dual is either feasible or, sorry, if the primal is feasible and bounded, it prevents the dual from being unbounded. But it still allows the dual to be feasible or infeasible. It can be feasible bounded, or it can be infeasible.
I see. But if the primal is feasible and bounded and the dual is infeasible, then strong duality doesn't, like, there is some optimum from the primal, but the dual doesn't help you find.
No, sorry. What I meant to say was if the primal is feasible, the dual can be infeasible because the primal can be feasible unbounded, and then the dual is infeasible.
I see.
Right? So that's the minus infinity case.
I got it, yeah. Got it.
Okay? But if the primal is both feasible and bounded, then I think the dual will also be, sorry, then the dual, let's see, does that force the dual to be? Yeah, I think the primal being feasible and bounded forces the dual to be feasible. Because if the dual is infeasible, then I think you're going to get an unbounded primal.
I see.
Okay? But it is possible for them both to be infeasible as well.
I see. All right. Yeah.
Okay?
Thank you.
All right, let's resume. Now we are going to mostly formalize All right, so now we are going to mostly formalize this proof. I'm sure there's still little details left, but I'm definitely going to give you enough of the formal structure that you can make it as formal as you want to. Okay? Okay? So remember that we've got this optimum, y star, for the minimization problem where we want ya to be greater than or equal to c. Okay? Again, I mean, the way you figure this out, the way I figured it out 20 years ago, I mean, I wasn't the one to invent it, but what I had was the physics proof. And so the way you sort of turn that into a math proof is you're aware that there's this important focus on the tight constraints of the linear program. Okay? So what we're going to do is choose a maximal subset S of the tight constraints. Oh, sorry, missed out a word. A maximal linearly independent subset of the tight constraints, A sub I. Okay? If you think about it, really the only part of the linear program that should matter is the part that's tight at the optimum. So that's what we're going to focus on in the proof. Okay? Everything else is a distraction. Now, another distraction is if you have non-linearly independent tight constraints, right? I could draw some more constraints that also go through the optimum point. And they're just confusing and distracting, right? And they're irrelevant, okay? Because if you get a bunch of linearly independent constraints, they define the position of the ball. And that means that the other constraints are automatically satisfied. Okay? So I'm going to call this set S. Notice that the size of S is less than or equal to the dimension of the dual. Now, remember, at the start, I said that n is the dimensionality of the problem and m is the number of constraints. But when we take the dual, the constraints turn into variables. So the dimensionality of the dual problem is going to be the number of constraints in the primal problem. Okay. Okay, so that bounds the possible number of these linearly independent constraints. And now I'm going to let AS be just those columns. And I'm going to let C sub S be the corresponding bounds of those constraints. Okay, so I'm going to drop all of the slack rows, slack columns, and I'm going to drop the linearly dependent ones, right? So what this means is that A sub S is going to have full column rank because I chose the columns to be linearly independent, right? And we're also going to have that y times A sub S is going to be equal to C sub S, right? Because they're tight, right? The general constraints are that y is greater than or equal to c, but we're now focusing on tight ones, so we have equality. Okay. Now, we also have that yb is equal to the optimum. Can anybody tell me why? So in other words, what I'm telling you is I've thrown away a bunch of constraints. I'm only looking at the constraints in S. I'm saying that my y is still optimal, even though I've thrown away a bunch of constraints. Why is that? Yes?
Be totally formal, but the idea is like it's still a local minimum, and because it's convex, it should still be a global minimum.
So the question is, how do I know that y star is still a local minimum? Right? In order to be optimal, it has to be a minimum. So how do I know that it is? Yes?
The concerns that you threw away are the ones that didn't matter?
Exactly. I threw away slack constraints. Right? I can't suddenly get a better optimum when I throw away a constraint that wasn't even tight. Right? If throwing away that constraint gives you a better optimum, then I can put it back and I'll still have a better optimum. Okay? Similarly, for the redundant constraints, the ones that are linearly dependent, right? The value of those constraints is determined by the value of these constraints because they're spanned by these constraints. So taking them away doesn't matter either. It doesn't give me any more flexibility. Okay? So what I've done here is gotten rid of distractions. Okay? I now have a new linear program involving only these important constraints. And y star is still the optimum of this linear program. So what I'm going to do is I'm going to show that strong duality holds on this linear program. Okay? Via some x star such that AS times x star is equal to b, and x star is greater than or equal to 0, and cx star is equal to y star b. Okay? That's what I need to prove. I need to prove that there is such an x, and then I will have proven strong duality, right? Okay, that proves strong duality for A sub s. How do I get back to strong duality for A? Right? So here, we're looking at C times x star, right? Sorry, CS times x star. Remember that CS is only some of the variables of C. Right? If I want to prove strong duality for the original linear program, right, I need more xi's. I need xi's that go with the other parameters from C. What should those xi's be? Yes? 0, right? So on the redundant constraints, I'm just going to make xi equal to 0, because then, right, ax, if I bring in those other 0 xi's, is going to be equal to as times, is going to be equal to as, a times x star is going to be equal to as times x star because the other x is just 0 out their columns, rows, 0 out their rows in the matrix, right? And cx star is going to be equal to c sub x for the same reason. And so we'll have strong duality for the original problem. Okay? So again, all this is doing is saying you only need to prove strong duality when you have linearly independent constraints that are all tight. And then you get this, then you just put zeros. This is again complementary slackness, right? You put zeros on all the slack constraints. Okay, so given that we've reduced to this case of linearly independent columns and full column rank, I'm not going to use S anymore. I'm just going to talk about A. Okay. So my first claim, and again, this is just following the physics. So what's the first thing that we proved from the physics? That there exists an X star such that AX star is equal to B. Right? We proved that the forces are in balance. We proved that by physics. Now we need some math. How can we prove this in math? Well, let's suppose not. If there is no X star such that AX star is equal to B, what can we possibly conclude from that lack of a solution? I will give you a hint that the answer is on the board. Right? If you don't have a solution to a linear system, then what do you have? Yes?
Matrix is singular?
Your matrix is singular. So we actually defined A to be a matrix with full column rank. Right? But what do we, so I mean, are you saying you directly get a contradiction? That may be true, but I don't remember enough linear algebra to know. Yes? Yes, but suppose that it is, right? I mean, there we go. Look up on this board. Why did I do duality for linear systems first? So that I could have it on the board now, right? If there is no x such that ax is equal to b, then there exists a z such that za is equal to 0, but zb is not equal to 0. Okay. So we're going to use that z to derive a contradiction. Okay. First of all, notice that right here I have a non-zero zb. Right. If it's negative, if it's positive, I can take minus z and make it negative. So I'm going to assume without loss of generality that in fact zb is less than 0. Okay. So again, what would it mean in physics if there is no x star such that ax star is equal to b? What would that say about our physical system? Yes?
The ball's on balance?
The ball is out of balance, right? It's saying that there's no way to balance the force of gravity with the hyperplanes that you have. Now, if you can't balance the force of gravity, what's going to happen? The ball will move. Okay, so that's how we're headed towards the contradiction. Okay, so let's consider our original ball position with the shift that is suggested by the linear system duality. Okay. I claim that this new point is feasible. Can somebody prove to me that this is a feasible point? Yes? Exactly. Y prime A is equal to y star plus z A, which is equal to y star A plus 0. So we have exactly the same value y star a. And if you remember, that's actually equal to c. And so it certainly satisfies the greater than or equal to c feasibility conditions. Yes? What is the value of the objective function? So that's going to be y prime times b. Yes?
Better because like, oh, y star b plus bt, so it's better.
Exactly. We again expand this into y star b plus zb, right? Which is, well, we made zb less than 0, so this is strictly less than y star b, right? Which means it is better than the optimum. Okay? So again, this is just a mathematical formalization of the fact that if the hyperplanes can't hold the ball in place, then the ball is going to go down, and you'll have a better height, a better objective. Okay? So we derived a contradiction. And therefore, the claim is proven. There is a way to balance the forces. So the next claim is that yb is equal to, or y star b is equal to cx star. Okay. And that one's actually trivial, right? We know that ax star is equal to b. That's what the claim said. We also, by construction, have that y star a is equal to c. Right? That's how we that's how we picked our columns. Okay. And that, of course, means that y star b is equal to y star times ax is equal to y star a times x, which is equal to cx. So the two objective functions match. And again, this really starts to show what the challenge is in linear programming. The whole challenge in linear programming is to ask which constraints are tight at the optimum. Right? If you know the tight constraints, if you can ignore the other ones, then you get equalities everywhere, and everything is very easy to analyze. Right? It's the inequalities that come from the loose constraints that makes things tricky. Okay. So there's one last thing. Again, we're just following the physics. One last thing that we have to prove, which is that all of the xi star are greater than or equal to 0. Right? This is the other requirement for feasibility in the primal linear program. And the physics is we need to prove that all the forces are positive, that none of the walls are pulling on the ball. Okay? So again, we're going to work by contradiction. Let's suppose that some xi is less than 0. Okay? And again, this takes us into this very bizarro physical world where the force that a wall exerts on a ball is negative. Okay? The ball is pulling on the ball. So now let's go back to what I was saying about sensitivity. Right? So I was talking about how the x's measure the sensitivity of the ball's height to changes in the position of the constraint. Right? And if x is very positive, that means that when you move the constraint upwards, you make the constraint tighter, it's going to make the ball go higher. Now, what would it mean if x were negative? Well, it would turn things upside down. It would mean that if you move the constraint, if you make the constraint tighter, if you push the wall higher, the ball gets lower. And that doesn't make any sense, and that's what we're going to prove mathematically. Okay? So what I'm going to do is I'm going to imagine moving the constraint. Okay? I'm going to make a new constraint vector, okay, which is equal to the old constraint vector, but I'm going to add the ith basis vector. Okay? What does that mean in physics? What am I doing if I add to Ci? I'm pushing the wall forward, right? Which intuitively, at least, should be raising the ball. Yes, because I'm making the constraint tighter. There are some positions that were valid for the old constraint, but once I make the constraint bigger, they now violate the YA greater than or equal to C constraint. Yes? So what does this do to the linear program? Well, let's consider solving the linear system YA equals C prime. Okay? So again, going back to the physics, all I'm doing is saying move the constraint, and now tell me where the ball is. Right? Because again, all the constraints were tight. We downsampled so that we only had tight constraints. Right? And now I'm moving one of these constraints to make it tighter. And so I'm asking the obvious question, where do all of those constraints intersect? Because that's the new optimum. Okay. Now, can I solve this? Do I know that there's a solution? I mean, not every linear system has a solution. Well, in this case, I can because of the way I chose the columns of A. Remember that I said that A has full column rank. Right? So there is always a solution. Which is just saying that there's enough information in the tight constraints that there's just a single intersection of them. Okay. Now we defined C prime to be bigger than C because we added 1 to the ith coordinate. That of course means that y prime times A, which is equal to C prime, is bigger than C. And what does that mean in words? It means that y prime is feasible for our dual LP. Yes? But what is the value of the objective function? Well, I redo what's up here. Okay. Y prime times B is equal to y prime times AX, which is equal to y prime A times X, which is equal to, put that in parentheses, right? Which is equal to C prime times X, right? Which is equal to CX plus what? Yeah? Xi, right? Because the only change in C prime is that we added to Ci, right? But what do we know about Xi? Negative?
C are positive, but Xi is negative. The adding Xi reduces the objective, is what I'm trying to say.
If that happens, then I may have flipped a sign. Let's see. We are trying to minimize y, right? Oh, yes, sorry. We assumed xi is less than 0, right? So since we assumed xi is less than 0, this is less than cx. What does that mean? Right? Remember that cx was equal to yb. So if we find something that's smaller, what does that mean? Yeah?
We violated weak duality.
We violated weak duality. Or, well, I wouldn't put it quite that way. But we got something that's better than opt. Right? The whole definition of, I guess, sorry, again with my stars, the whole definition of y star was that it was the optimum for the linear program. Right? And what we just, if one of the forces was negative, what happens is that when we raise the constraint and push on the ball gets lower and improves on the optimum value of the height, which is a contradiction. So that tells us that actually all of the x's have to be non-negative, which tells us that the x star that we found by looking at the forces generated by the hyperplanes is a feasible x star for the primal linear program. And it has a matching objective value, and that proves strong duality. Okay. Any questions? All right, so you've got the physics, which I think provides a good deal of intuition. And hopefully you see how this is literally just turning that physics into math. We're not applying any new mathematical ideas here. We're just taking every step of the physics and seeing how do we express that mathematically. Yes?
Given the optimum for the primal, is it easy to construct the optimum for the dual?
Oh, that's a wonderful question. It's so good that we're going to put it on your homework next week. Okay. But that would make it bad if I answered it now, right? Or I guess for you it would make it good. But all right, so yeah, as we're wrapping up, let me show you an interesting corollary. And this is a corollary that actually interferes with my sort of approach to solving problems, right? So when we talked about how you solve combinatorial optimization problems, I said, well, first you look at the structure of the solution, and then you ask about which solutions are feasible. And once you have feasible solutions, then you start talking about checking for optimality and then finding optimal solutions. But look at this really bizarre corollary of strong duality. Okay. For linear programming, finding an optimum solution is exactly as hard as finding a feasible solution. Okay? In other words, an algorithm for optimizing a linear program can be used as an algorithm for finding a feasible point. That's not surprising. But also, an algorithm for finding a feasible point of a linear program can be used to optimize any linear program. Okay? So the easy direction first, if I want to use optimization for feasibility, I can just optimize 0 times x, right? I just make up an arbitrary objective function and say, find me the optimum of this objective function, and it will have to give me a feasible point. So that will solve the feasible problem. Much more interesting is the opposite direction. So suppose that I'm now going back to my usual formulations. Suppose I have this problem of minimizing cx such that ax is equal to b and x is greater than or equal to 0. Okay? This is an optimization problem. If I only have a feasibility algorithm, I can't see how to solve it yet. Okay? But let's also write down the dual, right? Max of yb such that ya is less than or equal to c. Okay? This is also an optimization problem, and it's not clear how I can solve it using only a feasibility solver. Thank you. Ya is less than or equal to c. Okay? But now comes the trick. How can I take these two optimization problems and instead make a feasibility problem that gives me the answer to the optimization problems? Yes?
You put that into like a single problem and set cx equals to y.
Exactly. I just put them together and say, yes, I need an ax equals b, and an x greater than or equal to 0, and a ya is less than or equal to c. But now I just add strong duality, which is, after all, a linear constraint. I say cx equals by. Right? So all I've done is I've added a constraint saying whatever feasible points that you find have to satisfy strong duality. And we know that they exist because we've just proven strong duality. Right? And we also know that if you find this solution, then these 2 points prove each other's optimality, because each of them is a bound on the other, and they're tight. Okay? So that's pretty amazing, right? There's this bizarre equivalence, thanks to strong duality, between what seems like a much harder problem of optimizing a linear program. It's really the same as just finding a feasible point. Now, this is a theoretical result, okay? And it applies if you have a general purpose linear programming solver that can take any linear program, okay? Now, it is not something that you will want to apply at all times, because there are many cases where you get linear programs that are easier to solve than the general case. For example, MaxFlow, right? MaxFlow can be expressed as a linear program, and we'll do that next week. We'll do that on Monday, right? But the algorithms for MaxFlow are very specialized and do not solve arbitrary linear programs. Okay? So if you did the transformation, say, let's take the MaxFlow linear program and turn it into a feasibility problem, right? You can turn it into a feasible linear programming problem, but it won't be a MaxFlow problem anymore, and so you won't be able to use the MaxFlow algorithms. So this does not give you a transformation from MaxFlow to feasible flow, for example. Okay? But it does give you this very general transformation that applies for arbitrary linear programming solvers. So again, this has been the mathy lecture of the course. No algorithms anywhere in sight. We're finally done with that. On Monday, we're going to get back into algorithmics. Monday is going to be devoted to the practical aspects of taking duals and thinking about them. We will write down a bunch of combinatorial optimization problems. We will then figure out how to take their duals. And what we'll discover is that when you take the dual of a combinatorial optimization problem, you get enlightenment. Right? It's sort of just the process. It's really interesting. Just the process of taking the dual gives you, like, literally a different perspective on the problem, right? Because the dual it has the same optimum, right? And it's got the same structure in it. It's just turned upside down or turned sideways, transposed, right? So you get this completely different formulation of the same problem, which can give you a lot of insight into what's going on. So that's what we'll see on Monday. See you then.